Assalamu alaikum everyone. My name is Ismail Sheikh Noyon. I am from the Department of Tripoli, University of Scholars, and I am from the regular 11 batch. My course is Digital Electronics, and in this course my presentation is about the shift registers. So let's get started. What is a shift register? Now, a shift register is a type of circuit which we use to do the arithmetic functions. Now, in arithmetic functions, there are plus, there are minus, there are multiplications, and there are divisions. And a shift register can store n bits of data. So, it can store multiple bits of data. Now, because we are talking about data, I want to discuss about something electronic basic. Electronic basic. So, as we know that in a very simple circuit, if I draw a very simple circuit right here, now this is a circuit containing a switch, a battery, and a bulb. Now, in this condition, the bulb is off because the switch is off. The switch is open. This circuit is called an open circuit. And this condition, we can say that off condition. Same goes for when I close the switch, now the bulb is turned on. In that case, I can call this circuit a closed circuit, and I can call this condition as on condition. Now, if I take the off condition and on condition in case of the voltages, then we are saying that in the off condition there is low voltage, and when it is a closed circuit, then we are saying that it is in the high voltage, high possible voltage. Now, we use binary digits to explain these two conditions. In case of the off condition, we call it 0. In case of the closed condition, we call it 1. Now, this 0 and 1, these two things make what we call the binary digits. And in the electronic circuits, by using the electronic circuits, we can store these binary digits only. These binary digits only. Now, before I go to talk about more about the shift registers, I would like to discuss about the signals also. Now, an electronic circuit actually uses a digital signal. A digital signal. Now, what is actually a signal? A signal is actually a time varying voltage. So, in the signal, there will be higher voltages and lower voltages depending on the time. In electric circuit, we use digital signals for computing. In case of digital signals, there are only high signals and there will be low signals. So, the signals will look like that. The higher signals, we will identify them as 1, and in case of the lower signals, we will identify them as 0. We can use this method to carry what we call information. Now, so we can say that signals actually carries information. Now, information is made out of data, and the data that we can actually store in an electronic circuit is actually the binary digits, zeros and ones. So that's how we can actually save any kinds of data in the form of binary digits. Now, because we are talking about data, we have to know about another circuit which is called flip-flops. Now, flip-flop is a type of circuit that that can stay in two stable states, which is used to store binary data. Now, it uses a clock signal and it can flip or flop over the time. Because of its two stable states, it is called a flip-flop. Now, flip-flop has its own explanations, but I am going to introduce to you to the basic flip-flops only, because the shift registers are actually made of flip-flops. Now, in the flip-flop, as we know, that a single flip-flop can store only 1 0 or 1 1. It means it can store only a single bit of data. In case of the flip-flops, let me draw a flip-flop right here, D, Q, clock. Now, this is input, this is output, this is clock. A single flip-flop can store only one data. Either it can be 0 or it can be 1. And the data can be changed when we are adding a clock, so the data will change according to the clock transitions. Oh, what is actually clock? What is actually clock? Clock is a type of signal. So if you want to understand clock, you have to understand something named a synchronous system. Synchronous system in which the clock actually synchronizes all the ICs. Now, in a synchronous system, a clock is actually another signal which actually turning off the circuit or turning on the circuit. Let's say that this is a 1 GHz clock signal. Now, what is a register? Right? What is a register? As we know from the flip-flops, it can store only a single bit of data. Either it can be zeros or it can be ones. But how about these bigger binary digits? Let's say 1011. This binary digit is made with 4 bits of data, this binary information. But the flip-flop can only store single bit. To store this information, we will be needing 4 flip-flops. Or let me break it down to you like that. Imagine a water cup containing a cup of water. If I say the water is my bits, then this cup I can consider it as my flip-flops. If I want to store 4 times the water, I would be needing 4 cups. Or I can use a bigger beaker or a jar to store the same amount of water. So, to store that amount of water and also by maintaining the same clock speed, we use the registers. Now, it is a group of flip-flops which stores n bits of data, and all the flip-flops share the same common clock, what we call a master clock. Let me draw our registers. Now, one thing I didn't tell you, that why we are using a D flip-flop right here, not the other flip-flops. Because in a D flip-flop, there is only one input and one output. And it is changeable by adding a clock. Now, if I use 4 flip-flops, 4 D flip-flops, I can make what is called a register which shares a same clock, means a same clock or a master clock. Now, when we are giving input in every flip-flops, the data is stored when a clock signal is being generated. But this register is actually useless. Why it is useless? Because in a synchronous system, let's say that I have given input a clock speed of 1 gigahertz, which means 1 nanosecond, the clock is interchanging. Now, let's say that I want to store a data for 300 nanoseconds. I can store it right here because every time the clock is changing for 1 nanosecond, inside the stored data is also changing. So that is why I can't store a data for 300 nanoseconds here. So now I can think that I can control, if I control this clock, will it solve my problem? No, it's not going to solve the problem, because in a bigger system, imagine that this is 3 systems, 1, 2, 3. They share actually a same clock, or we say it a master clock. So in a synchronous system, if we try to control the clock, it will not be synchronous, because all the systems can communicate in a synchronous system like this. Now, if I can say that what if I put an AND gate right here, an AND gate right here, will it solve my problem? It's not going to solve my problem either. It is because I am also, in that case, you can say that I can control the clock, right? Like if I put my input right here, like if I input, if I give one input clock 0, then it's going to be 0. I'm going to be 0. 0 input 1, it's going to be 0. If I give input 1 clock 1, it's going to be 1. Okay, so I can say that I can control this register, control this clock by adding an AND gate. But this thing is actually very impractical. Now, usually in a 4-bit register, we use some gates to actually store the data. In that case, we actually use a OR gate and to AND gates. OR gate and to AND gates. Let's say that this is my load and this is my input. Now I have to draw 4 more for each of the flip-flops, so I am skipping that part. Now let's see, this is my load and this is my input. When my load is going to be high, here I will see 0. And because of that, this AND gate is actually off. And in input, I am getting 1. And this one, because this AND gate is now activated, this is going through the OR gate and then in the clock. So now, from the output of the clock, it is going back to the AND gate. Actually, it is going back to the AND gate. So that's how a single flip-flop in a register is storing a bits of data. But if you see right here, this is more complicated because it needs lots of gates, lots of connections. So that is why we use shift register. How we use shift registers to solve this problem? In a shift register, what we actually do, we actually put the input right here, the output of one flip-flop to another one's input, this one's output to another one's input, this one's output to another one's input. That's how a flip-flop actually works. To demonstrate the shift register, I am using what I call SISO shift register, or serial input, serial output shift register. Shift register. Now, let's say that these flip-flops are controlled by one master clock. Now, let's say that I am giving an input of 1, 1, 1, 1. If I give input 1, 1, 1, 1, now first of all, for the first clock, the input from here will go here. In the second clock, the input will go from here to here, and another one will replace and come here. And then when I give a third clock, let me draw the clock for you. So first clock done, second clock. Now the third clock. When I am giving the third clock, the third digit is coming here, another one is replacing here, this one is replacing here, and this one is replacing here. So that is how for the 4 clocks we are getting 1 bit of data as our output. So for the last input, I would be needing 4 more clocks. So in the register, the problem was that to store our data, we have to use multiple cycles. But by using only 4 clocks, we can shift and store the data inside a shift register. Now, why and how we can use the shift registers in a arithmetic function. So, in arithmetic function, there are plus, there are minus, there are multiplication, and there are divisions, right? These functions. Now, let's say that I want to multiply something. Let's say 2 into 4 equals to 8. I want to multiply this thing. I can do this by using an adder circuit. To use adder circuit, I have to add 2 plus 2 plus 2 plus 2 equals to 8. That's how an adder circuit actually adds and does my multiplication. But the problem is that if you see right here 2 plus 2 plus 2 plus 2, for each of them I am using a single adder. So it is also making my circuit more complicated. So that is why we use shift register. And in the shift register there is left shifting and right shifting technique. Now let me draw the flip-flops as the boxes, as the blocks. Let's say I am going to do the right shifting. First, let's do the right shifting. In right shifting, in that case, when I am using the first clock, let's say that let's draw a table Q1, Q2, Q3, Q4. Now, for the first clock number 1, the 1111, let's say this is our input, okay? Now, for the first clock, first bit is going here. So first bit is stored right here. Other blocks will remain 0, 0, 0. So I will write 1, 0, 0 and 0. When I am giving it second clock, another one, this one will shift right here, 0, 0, and another one will come into the place. When I am giving third clock, it will go 1, 1, 1, 0. And when I will give the fourth clock, 1, 1, 1, 1. Now, as we know that because we input 4 clocks, I am getting 4 digits. Now I can read here. Here is my input that I can read. Now, if I want to read this, then I have to add a 5th clock. For this, I have to add a 6th clock. I have to add a 7th clock. That is how I can read the another data. Now I was talking about the left shifting and right shifting, right? How left shifting, by shifting left or shifting right, I can read a data. Let's say that when I'm shifting like this, I'm shifting in the right. In that case, it will be 1, 0, 0, 0. In second, it will be 0, 1, 0, 0. In third, it will be 0, 0, 1, 0. In fourth clock, it will be 0, 0, 0, 1. So this is equals to 1, this is equals to 2, this is equals to 4, this is equals to 8. So as we can see the decimal numbers right here, we can say by shifting in the right, we can actually do the division function. And now let's see what we can do if we shift left, right? Then the result will be like this: 0 0 0 1. First clock come here. First input came here for the first clock. In the second clock, the input is jumping right here. So it will be 0 0 1 0. In the third clock, the input is going here. So it will be 0 1 0 0. And in the fourth clock, it will be 1 0 0 0. If we convert them into the decimals, we will see 1 2 4 and then 8. So it is actually multiplying the functions. So that is how, by using a shift register, we can easily do multiplications and divisions. Moving on, that how a data can be loaded in a shift registers. There is two ways a data can be loaded into a shift register. That is, one is in the serial in and another is in the parallel in. I will show you like now. Let's say that let me draw it in a more specific way for you. Let's say that these are 4 D flip-flops, right? With one input and one output. Now, if I give input like this, it will be a series input. In that case, if I want to change an input in another place, in another flip-flop, or if I want to read the data, I have to wait for the another clock pulse, or I have to add another clock pulse. So that's how we can load a data. Another one is parallel input. So in this case, I am giving the input parallel, and in this case, for just a single clock, I can put 4 bits of data instantly. So in the series connections where I have to share or I have to use 4 clocks, I am only using a single clock to store 4 bits or n bits of data in a series connection, in a parallel connection. Now, how data can be retrieved? Like we can load the data, we can retrieve the data in serial out input and parallel out input. Now, if I want to take the data serially, I can take the data from right here. And if I want to take the data parallelly, I have to take the output like this. So, for each clock, I can have 4 bits of output, and for 4 clocks I can have a single data at a specific time in case of the series input, series output. Now let's talk about the types of shift registers. So the way we can load bits and the way we can retrieve the bits, there are usually 4 types of shift registers. There are CISO, SIPO, PISO and PIPO. CISO is serial in, serial out, SIPO is serial in, parallel out, PISO is parallel in, series out, and PIPO is parallel in, parallel out. Now let's talk about the series in, series out. The shift register that I was explaining a bit earlier was actually a CISO, or series in, series out shift register. In that case, all the inputs are in series and all the outputs are also in series. And here is the master clock. Now this is the truth table and this is the timing diagram of the series in, series out, seesaw shift register. Now let's move on to the SIPO or series in parallel out shift register. So in this case, the series, the input are in series, but the outputs, we are taking the outputs parallel. We are taking the outputs parallel. In this case, for one single input, we can receive 4 bits of data. And this is how the SIPO shift register works. This is the truth table and this is the timing diagram. Now, PISO or parallel in series out. This looks like a bit complicated, like the 4 bits register I talked earlier about. So this actually what it does, it actually allows parallel input. So it is taking parallel inputs, 4 bits of input, but it is giving just one output. So for 4 bits of input, we are actually receiving single output. And at the last, we have the PIPO or parallel in, parallel out. In this case, what actually happens that we are taking data, 4 bits of data parallelly, and also we can measure 4 bits of data in the output. Now, I am going to show you a table. This table is actually based on the loading, the reading, and the clock we need, the amount of clocks we need to retrieve the data. So by using this table, we can actually by using this table, we can actually find out that how many clocks we need in different kinds of systems, shift registers, and in different modes to have the clocks. The amount of clocks we need to retrieve the information. Now I would like to talk about the applications. Now, shift registers are used for temporary data storage. Shift registers are also used for data transfer and data manipulation. The series in, parallel out shift register is used to convert serial data into parallel data. Thus, they are used in communication lines where demultiplexing of a data into several parallel lines is required. A parallel in social out shift register is used to convert parallel data to serial data. Now, I'd like to thank you so much everyone for listening, and I'd like to thank our course teacher for giving me the opportunity for this presentation. I hope you will all like it. Thank you so much.